Well, good morning, dear. Welcome back. And you have started watching the videos on support vector machine. So now we are going to discuss, it is a continuation of my earlier lecture. We are trying to clarify the concept of kernel trick. This is actually, I'm sorry, this is M cross M matrix. Okay, so you have seen that the kernel trick take the advantage of this feature mapping, and being in the same dimension, it gives the fruits of high dimension and makes your computation very friendly. So now how to design the kernel, okay? How to make the kernel, right? So it is actually intuitively, you see you have two class samples x and z. If the vector x and z are similar, then the kernel k xz will be large, because similar means the dot product between them, the cos theta angle will be closing towards 0, so making that is large. And dissimilar, if x and j's are dissimilar, obviously say this is your x and this is your z, okay, and then dot product between them will be 0, tending towards 0. So earlier the dot product between similar vectors is towards actually is similar to 1, and dissimilar vector is 0. So seeing the class representative samples behavior, my kernel should be able to capture that. Okay, so not everybody can be a kernel, right? So you see, this is the concept of kernel is clear right now. Kernel trick is also clear. So now let us see, with that intuitive concept, how you can actually design your own kernel. You need not, because so many people have already done a lot of research and developed many using kernel trick, many standard kernel function which you can use, but nevertheless you should know that they should have anything cannot be a kernel function, say Gaussian kernel. This is the definition of Gaussian kernel. You see, as I told earlier, that if x and z are similar, then that kernel function should tend towards 1. You see, this is similar means towards 0, and e to the power 0 is tending towards 1. And if x and z are dissimilar, then this should tend towards 0. Okay, so e to the power this is dissimilar, x minus z is dissimilar, that it should be tending e to the power a very large quantity should be tending towards 0. So Gaussian kernel passed that test, intuitive test. Okay, so it could be a valid kernel. Similarly, radial basis function kernel also pass the test. Okay, and your another kernel is polynomial kernel also will pass the test, that is kxz equals to, you see, if they're similar, this will be dot product will be equals to tending towards 1. Exactly 1 to 1 will not be there, but tending towards 1. And if they are dissimilar, this will be tending towards 0. So that means that concept of small and large should be accommodated by a kernel function. So if you want to design your own kernel function, that should also obey this kind of intuitive properties. Then another more formal way of of making a kernel is that all kernel must obey Mercer's theorem, which is telling that if k to be a valid kernel function, so these are actually kernel functions. So these are kernel functions, and this is kernel matrix, okay, which is a square matrix, and so this is a kernel function, okay. So kernel function is doing this job, okay. So this could be your Gaussian kernel, linear basis kernel, or whatever, right? So in the algorithm, you will actually compute this, See, it's very, very important to know that that is the difference between kernel function and kernel matrix. I hope it is clear. So this is kernel function. All these elements actually are the elements of this matrix you are getting using a kernel function and making dot product with the samples, okay, which you have for training. So k to be a valid kernel function, there must exist phi, that is a feature mapping function phi, so that we can express k xz equals to the phi x transpose and phi z, that is a dot product between this mapping function. So it must be equal to the kernel xz, okay, and correspondingly kernel matrix K must be symmetric and positive semi-definite. That means K should be greater than or equal to 0. That is, all eigenvectors actually will be greater than or equal to 0. Eigenvalues actually greater than or equal to 0, that we have mentioned here. So eigenvalues lambdas will be greater than or equal to 0. Being constituted from a finite data set, M should not be infinitely large, set of M points, and having dimension M cross M with its ij entry is given by Kij is this, okay. So this is exactly what you know. So Kij is the element of this matrix, this is a kernel matrix, it is a M cross M matrix for M samples, okay, and it should be positive, semi-definite, that is eigenvalues greater than or equal to 0, and the nature of the matrix should be this, okay. So not everybody can be a kernel, okay, kernel function. That kernel function should generate this kind of kernel matrix, okay, which will satisfy the condition. Mercer's theorem is telling that. Now let us try to prove. It's very simple. Let K is a valid. So proof we will do like this. Instead of proving directly, we are assuming at the beginning that K is a valid kernel corresponding to some feature mapping phi, feature mapping function phi, and now we are considering some, say, n number of points that not necessarily be the training samples, and let a square matrix K M cross N be defined such that its ij entry is given by Kij. Kij is equals to Ki dot j, okay. So this is what, okay, and the matrix, this matrix is called kernel matrix, okay. Now if so, it is now clear, right? What is a kernel matrix, what is a kernel function is now clear, seeing this one, okay. Okay. And now if K is a valid kernel, K to be a not every matrix, symmetric matrix will be square matrix will be a kernel. So if K is a valid kernel, then its matrix Kij should be equals to Ki dot Kxj equals to phi x I transpose phi xj equals to phi xj transpose phi xi equals to kx xj comma xi, okay, xi. So this is the dot product. This is the symmetric nature of this matrix. It should be there if K is to be a valid kernel, and we are assuming that K is a valid kernel, and then we will see that what it is leading to us. Also, we are letting, because we like to do this matrix multiplication, okay, K phi kx to denote the kth coordinate of the vector phi x, and then for any arbitrary vector z, we can write z transpose k z, right? And that equals to, by the definition of matrix multiplication, we can write I j summation over I j z I k I j z j equals to summation I j k z I phi. So this if this is a kernel, then there must exist phi, so that phi x I transpose dot phi x I j, in place of that we wrote, okay, and z j. And then we are trying to expand, perform that matrix multiplication. So you know, matrix multiplication performing means you have to replace it by summation over k phi k x I, means you will have to two vectors are there, elements wise you are just xi zi x2 z2, so xi dot zi plus x2 dot z2 plus x3 dot z3, like that. Okay, so this is what we are performing with the summation sign here. Okay, and you all know that this is what matrix multiplication, A transpose B equals to summation of k AK BK. So that's the summation we did. And then taking this here ij, we are rearranging just algebra zi phi k x I dot phi k x j z j equals to summation over k. You see this repeating, okay, so we are making it square, and this, what is this, whatever may be the value of this has to be, since it is square, it is greater than 0, and summation, okay, so each term, square term actually can be greater than 0. So this is greater than 0. If this, what is this? This is actually z transpose k z. So z square is greater than 0. So k has to be also greater than 0. So that proves that k is a positive semi-definite. That is, all its eigenvalues lambda I greater than equal to 0. So we have indirectly proved that we assume that is a valid kernel, and then we prove that the all the eigenvalues of this valid kernel matrix is greater than equal to 0. Okay, so this is, it turns out to be that this is sufficient condition also. It's not only necessary and sufficient condition of k is this. Okay, so other way round, that if a matrix is giving with positive semi-definite, can it be a kernel? Can also be proved that if there exists, you will have to find that, okay, it can be a kernel if there exists a mapping function, like that. You need to, that we did not do here. We assume here k is a valid kernel, and then it led to that it's positive semi-definiteness. Okay, that's great. So you have now understood that how kernel actually can be developed. Okay, so this you can all the valid kernels has to follow these conditions, and then we can consider them as a valid kernel. So kernel actually is really changed the world of machine learning, the way we think about it. You see, kernel concept is making all linear classifier capable of classifying nonlinear problem as well. So can we not apply? It's very general actually. So generalized kernel method are being actively researched, and people are finding that yes, solutions are there. That means we can extend linear regression for regressing the nonlinear samples also, and then logistic regression, linear regression, perceptron learning, all these discriminative models which you have learned so far actually were confined to regressing or classifying the linearly separable problem only. But it turns out that using the same concept of kernel is what? You are taking a data which is linearly not separable to a higher dimensional feature space with a trick, kernel trick, where they are linearly separable. And you apply linear regression, logistic regression, perceptron learning, okay, which can actually learn and classify linearly separable problem there, okay, and you train there and in the higher dimensional feature space, and also test there, okay. So it works pretty good, and only thing you will have to do, you will have to modify these algorithms so that there should be a dot product in the training samples. That is called kernelization of linear regression, kernelization of logistic regression, kernelization of perceptron learning. All things you need to do a little modification so that in your learning algorithm something like this should be there. You see, dot product. You can see, yes, kind of dot product should be there. Your learning algorithm should be modeled in terms of that. That is called kernelization. Okay, so we can kernelize linear regression, logistic regression, perceptron learning. Not only that, next you are going to study another two generative models, very elegant. That is principal component analysis and linear discriminant analysis. And it turns out that here also they are actually applied to, they are called linear model, but using kernel concept, generalized kernel method, we can also apply PCA, which is a great dimensional tree reduction technique to a nonlinear data set, okay, both PCA and LDA. And we are going to discuss in detail about this. So here is some, we will conclude that what are the properties of support vector machine now. You have seen support vector machine has very good property, like a large data set. Normally for large data set there will be handful of support vectors, okay. So they are actually supporting that, specifying the separating hyperplane. It is also capable of handling large feature space, okay. However, computational complexity does not depend on the dimensionality of the feature space. So that is the most interesting, most beautiful thing, right? That computational complexity does not depend on the feature space dimensionality. That is all about kernel trick. So, okay, some flexibility of choosing kernel function, so you can use your out of many standard kernel, Gaussian kernel, radial basis function kernel, polynomial kernel, all kind of kernel function you can choose, and also that using soft margin approach you can just check some overfitting, and above all it has a nice mathematical foundation. That classification problem here has been formulated as a constrained quadratic optimization problem, which is guaranteeing during training for tuning the parameters, which always guarantees the global optimal values, okay. So that's a beautiful property. And some limitations, well, it is sensitive to noise, yes. So as you have seen that, okay, you can regularize, but there are limit, okay. If samples are noisy, then its performance actually decreases drastically, okay. And it's a binary classifier. However, as I told in the beginning, that we can extend binary classifier like this to multiple, for classifying multiple classes. For example, with output m, learn m support vector machine. So there are m number of support vectors, okay, machine. So support vector machine is learning, giving output 1 versus not 1, all others, okay. So 2 learns output 2 versus not output 2. Okay. SVM sort vector machine M like that. Okay, learns. So if m number of classes are there, so one versus the rest, another versus the rest, another versus the rest. So in that way you can configure that support vector machine to classify multiple classes. Okay. Also, to predict the output of a new input, just predict with each support vector and find out which one puts the prediction the furthest in the positive region. Okay, so in this way you can and applications, there are so many applications. Okay, text categorization, image classification, then handwritten character recognition, handwritten digit recognition, the bioinformatics, protein classification, all kind of classification tasks you can apply support vector machine. Actually, there is a data set called MNIST data set. It is the state of the art data set. Okay, and they have beautiful data for hand digit character, that is 1, 2, 3 up to 9, 0, 1, 2, 3. Hand digit character recognition data is there. Using that, you can just design your support vector machine which can classify those handwritten digits. Also, there is a comparison of support vector machine with other classifier. You see, this is k nearest neighbor, well formulated, test error 3 to 5%. Support vector machine with Gaussian kernel with or you can take also 4th degree polynomial kernel, the test error drastically reduced to 0.5 to 1.5. Then neural network 2 layers, 300 hidden units, 3 to 4.5% test error. 6 layers running on GPU can reduce to 1. So you are now muscle power, showing the muscle power of computation. Then if you add support vector machine with that muscle power, that is CNN augmented with support vector machine, 0.5 test error. So you can see in all comparisons, support vector machine is very good, performance is very, very good. Okay. So at the end, this I would like to give you the references. That this is the natural statistical learning theory. Vladimir Bapnik did a wonderful job in introducing support vector machine concept and the kernel concept. So pattern recognition by Duda Hart Stock, and then free Coursera machine learning by Andrew Ng, MIT Coursera by Patrick Winson, and numerous other open source materials you can refer for further reading. And that's it. So we are coming to the end, and I would like to show you a small demo, because there are so many communities, there's so many softwares, right? So it is really making off-the-shelf software, that machine, right? You give your data, and then that's it. The classification is done. So I would like to show you just after this. I am going to show you a small demo using the Leave SVM community software library support vector machine. There are so many communities, and they are developing softwares for support vector machine. And you see here, you see these are the color. This belongs to one class, say yellow. Okay. Then say this is my another class. So beautiful samples. And let us run the machine. You see, maximum margin classifier is here. Okay. Now say I am now selecting, this is my samples, okay, and and this is my other class samples. Now I am making a little bit noisy samples, so it's bad samples, right? And then I am running SVM machine. Still it could classify optimally between these two class of samples. So it's great, and you can also run this and explore many other avenues at how to utilize kernel, different kind of kernels, and classify. So these are all possible. So now you know that how it is working. So I am just clicking some points, and then the machine is running. What are behind the scene, now you know all about it. So I wish you good luck, and you be a real expert in machine learning once you can master all the tools which you are learning. So with this best wishes, I suggest that you practice. Actually, I am defining a project. I have already shared it with you with data set and detailed hints. Please do that. So that will clarify many concepts. The algorithm, if you can implement, then it will be a great learning for you. Now there is a possibility that what kernel function is, kernel trick is, and then exactly where in the algorithm, SMO algorithm, you need to put your kernel is known to you. So now practice it. Please do that job, and visit my website where the assignment has been designed and given for you, and have fun. So good luck, and wish you all the best. Stay safe. Bye bye.